strong enough for the sky, trusted in space, compatible with the human body. This is titanium, element 22.
I want you to imagine a material that sounds like a massive contradiction, like something ripped straight out of a science fiction script.
Right, something that just shouldn't exist in reality.
Exactly. A metal that is significantly lighter than steel, but, rivals it in pure structural strength. It can survive the blistering, just intense heat of hypersonic flight at the very edge of the atmosphere. It basically laughs at oceanic rust and chemical corrosion. And here is the real paradox.
The biology side of it.
Yeah. It is so exceptionally safe and biologically inert that surgeons can permanently implant it directly into your jawbone or your hip.
Which is, it sounds impossible on paper, right?
Yeah.
Materials that possess the mechanical toughness to withstand the violent thermal shocks of a jet engine flying at Mach 3, well, those are rarely the kind of materials you want interfacing with delicate human biology.
Right, there's usually a catch.
Yeah, a strict trade-off. Usually you have industrial strength on one side and biocompatibility on the other.
But this miracle material isn't science fiction at all. And it wasn't engineered in some sterile, futuristic laboratory either. For millions of years, it was hiding right under our feet, locked away in, of all things, ordinary, unassuming black river sand.
Just waiting for us to figure it out.
Exactly. So today we are taking a deep dive into element 22, titanium. And I have to tell you, this is far beyond a high school chemistry review.
Oh, far beyond it. Titanium's story is this sprawling, multi-century epic. We are looking at ancient cosmic origins, decades of incredibly frustrated metallurgists, the intense engineering pressures of the Cold War space race, and, modern medical miracles.
So as you are listening to this deep dive, I want you to consider how many ordinary rocks you walk past every single day, just kicking them down the sidewalk.
Right.
Because the timeline of element 22 proves that the literal dirt beneath our feet might hold the absolute key to the next era of technology. We just have to figure out how to unlock it.
And to truly understand element 22, you kind of have to observe it in extreme environments. We're going to look at the crushing pressures of the deep ocean, the freezing vacuum of the upper atmosphere, and the atomic structure that actually makes this metal tick.
Yeah.
Because what we are really examining today is the mechanism of human innovation. How we learn to manipulate the hidden potential of the natural world.
Okay, let's unpack this. Because to understand how this metal eventually conquered the skies, we have to start with the fundamental mystery. Why did it take humanity so incredibly long to even realize it was there? We are talking about the 9th most abundant element in the Earth's crust.
Right.
Yet it was practically invisible to us for most of human history.
Yeah, and that invisibility really stems from its chemical nature. Pure silvery gray titanium does not just exist freely in nature. You can't, go pan for titanium nuggets in a stream like you would with gold.
Or just melt it in a basic forge like iron.
Exactly. It's a transition metal, meaning it has this highly reactive electron configuration that allows it to form incredibly strong bonds with other elements. So it essentially spends its natural life locked tightly inside minerals, specifically oxides like rutile and ilmenite.
And humanity just unknowingly lived alongside these rocks for thousands of years until we finally get a breakthrough in the late 18th century down in Cornwall, England.
Yeah, the blank sand discovery.
Right. There's this English clergyman named William Grigger. He was a remarkably observant amateur mineralogist. And he was walking along a quiet stream and spots this strange magnetic black sand. So he takes it back to his study, treats it with hydrochloric acid, and realizes there's an entirely unknown metal hiding inside this dirt.
It was a monumental observation.
Yeah.
He isolated what he called a reddish-brown calx, but he didn't quite take it over the finish line.
He left it hanging.
Yeah. A few years later, in 1795, a prominent German chemist named Martin Heinrich Klaproth independently investigates a very similar mineral from Hungary. And he also realizes there's a new element trapped inside. And he's the one who gives it a name.
And what a name it is.
He calls it titanium, after the Titans of Greek mythology. Those ancient, immensely powerful beings known for their raw, unyielding strength.
It is a phenomenal name. But here is the major roadblock. If titanium is the 9th most abundant element just sitting there in the dirt in England and Germany, why didn't ancient blacksmiths figure this out?
That's the big question.
Like, why weren't medieval knights forging ultralight titanium broadswords or riding into battle in titanium armor?
Well, the answer really comes down to thermodynamics and the atomic bond. Titanium has an overwhelming, just relentless chemical affinity for oxygen.
In previous discussions on this show, we might have called that a chemical bear hug, but I think that metaphor is actually a little too simplistic for what is happening at the atomic level here.
It is.
It's more like a highly complex, multi-tumbler magnetic lock.
That is a much better way to visualize it, yeah. When titanium bonds with oxygen to form titanium dioxide, the atoms share electrons in such a thermodynamically stable configuration that traditional smelting methods are completely useless.
Right, because normally you just use carbon, right?
Exactly. For thousands of years, humans extracted metals like iron by heating the ore with carbon in a blast furnace. The carbon would aggressively bond with the oxygen, pull it away as carbon dioxide gas, and leave the pure molten iron behind.
But if you try that trick with titanium ore,
It backfires completely.
it just doesn't work.
No, if you heat titanium ore with carbon, the titanium doesn't just let go of the oxygen. Instead, it reacts with the carbon to form titanium carbide, which is this brittle, incredibly hard ceramic. It's not a usable metal at all.
Wow.
Yeah, so even the best scientists in the 19th and early 20th centuries were literally pulling their hair out, trying to find an efficient chemical key to unlock this magnetic lock.
So, for over a century after it was named, we had this metal named after gods, but we were completely locked out of using it. It remained this frustrating scientific curiosity until the 1940s.
And that is when everything changes.
Right. With the invention of the Kroll process by metallurgist Wilhelm Kroll, this is the massive manufacturing breakthrough that finally cracks the lock. It allows engineers to produce pure titanium on an industrial scale.
And the ingenuity of the Kroll process is that it doesn't just try to force the oxygen away with brute heat. It uses a really clever two-step chemical displacement.
Okay, how does that work?
Well, first, you take the titanium dioxide ore, mix it with carbon, and blast it with chlorine gas at extremely high temperatures. The chlorine effectively sneaks in and replaces the oxygen, creating a highly toxic, volatile liquid called titanium tetrachloride.
Which sounds like an absolute nightmare to handle.
Oh, it requires intense industrial safety protocols. But once you have that titanium tetrachloride liquid, you move to step 2. You pump it into a sealed reactor filled with an inert argon gas to prevent any oxygen from getting back in.
Got it. Keeping the oxygen out is key.
Exactly. Then you introduce molten magnesium, or sodium. Now, the magnesium is even more reactive with chlorine than the titanium is. So the magnesium essentially steals the chlorine away.
Leaving the titanium behind.
Yes, leaving behind a porous, metallic mass of pure element 22, which the industry calls titanium sponge.
And the timing of the Kroll process is almost cinematic, because once engineers could finally mass produce this titanium sponge, melt it down, and forge it into pure ingots, humanity was staring right down the barrel of the Cold War and the space race.
The timing was impeccable.
We unlocked a superpower metal at the exact moment we wanted to break the sound barrier and go to space.
Yeah, and to understand why aerospace engineers immediately fell in love with it, we really have to look at what is often called the holy trinity of titanium's physical properties.
Right.
First, it has immense tensile strength. Second, it has a relatively low density, making it roughly 45% lighter than steel. And third, it has exceptional, almost unparalleled corrosion resistance.
Here is where the practical application gets really fascinating. Let's look at the Lockheed SR-71 Blackbird.
Oh, the ultimate example.
It really is. This is the legendary Cold War reconnaissance aircraft that literally looked like a futuristic spacecraft painted matte black. It was designed to fly well over Mach 3, that's 3 times the speed of sound, or about 2,200 miles per hour, at extraordinary altitudes of 85,000 feet.
And flying at those sustained hypersonic speeds introduces a terrifying engineering bottleneck.
Right.
Aerodynamic heating.
Because of the friction.
Well, when most people think of atmospheric friction, they think of rubbing their hands together. But at Mach 3, the heat is actually generated by ram pressure.
Okay, ram pressure.
Yeah, the aircraft is pushing through the atmosphere so incredibly fast that it violently compresses the air molecules in front of it. That rapid fluid compression generates intense, blistering heat across the airframe, pushing temperatures well over 500 degrees Fahrenheit on the leading edges.
Which completely eliminates standard aviation materials. I mean, if you build the SR-71 out of standard aerospace aluminum, which is beautifully lightweight, the airframe would literally warp, lose structural integrity, and melt mid-flight.
Aluminum's tensile strength just drops off a cliff once you pass 150 degrees Celsius.
And if you pivot to steel, you solve the heat problem. Steel can handle 500 degrees Fahrenheit with ease, but
But steel has a density of about 8 grams per cubic centimeter. If you construct an entire high-altitude reconnaissance jet out of solid steel, the airframe becomes so incredibly heavy that the thrust-to-weight ratio is completely ruined.
You would need an absurd, physically impossible amount of fuel just to get it off the runway, let alone push it to Mach 3.
Exactly. Every single kilogram is punished in aviation. So you need something that can shrug off the extreme thermal shock like steel, but mimics the lightweight properties of aluminum. And titanium sits right in that sweet spot.
Its specific strength.
Yes. The ratio of its strength to its density made it literally the only viable material on the periodic table for this job. It was the critical enabler of high-speed flight. The SR-71 was built of 85% titanium.
That's wild.
The metal's crystal lattice structure, it's a hexagonal close-packed formation at room temperature, gives it that incredible rigidity. It could survive the immense mechanical stress and the atmospheric compression heating without weighing the aircraft down. It pushed humanity through the thermal thicket.
And there's a famous anecdote about the SR-71 that highlights just how extreme this thermal expansion was. Because the titanium would heat up and expand so drastically during a Mach 3 flight, the engineers couldn't build the plane with tight, rigid seams.
They couldn't bolt it flush.
Right. They literally had to design the fuselage panels with gaps between them, so while it was sitting cold on the runway, the Blackbird would actively leak jet fuel onto the tarmac.
Just dripping fuel everywhere.
Yeah. It was only after it took off and reached supersonic speeds that the titanium panels would heat up, expand, and tightly seal the fuel tanks.
Which just perfectly illustrates the extreme environments we are talking about. You have a metal subjected to intense atmospheric violence.
Which brings me to the massive pivot in this story, because I find this to be the most mind-bending part of Element 22. We take this metal out of the vast, freezing vacuum of space, out of the extreme thermal compression of hypersonic flight, and we place it into an environment that is just as chemically complex, just as demanding, but vastly different.
The internal ecosystem of the human body.
Exactly.
It is a totally jarring transition. I mean, the exact same element used to forge rocket engine housings in high-altitude spy planes is routinely used in delicate dental implants, spinal fusion devices, and artificial hip joints.
But normally, if you introduce a foreign piece of metal into a biological system, the immune system orchestrates a massive attack. White blood cells swarm the area, fibrous tissue encapsulates the invader, and the body tries to reject it.
That's the standard biological response.
So how does the body just passively accept this intense aerospace metal without a fight?
Well, it doesn't just passively accept it. It actively welcomes it. And the mechanism behind this biological miracle connects directly back to that magnetic lock we discussed during its discovery.
Oh, the oxygen affinity.
Yes. The exact same overwhelming affinity for oxygen that made titanium so notoriously difficult to smelt is the secret to its biocompatibility.
So the curse becomes the superpower.
Precisely. When pure titanium is exposed to the atmosphere, or crucially to the oxygen-rich environment of human blood and bodily fluids, it instantly undergoes a process called passivation.
Passivation.
Right. In a fraction of a second, the surface titanium atoms react with oxygen to form a continuous, incredibly thin layer of titanium dioxide, usually just 2 to 10 nanometers thick.
So it builds an instant microscopic armor.
Exactly. This oxide layer is functionally a ceramic. It is chemically inert, it's thermodynamically stable, and it's completely impenetrable to the corrosive chlorides found in our bodies.
So the body doesn't actually touch the metal.
No. When a surgeon places a titanium implant into a femur, the patient's immune system doesn't actually see reactive metal. It sees this quiet, stable ceramic oxide shield. And because the shield doesn't release free metallic ions into the bloodstream, the body simply doesn't recognize it as a toxic threat.
That is amazing. And it goes beyond just avoiding an immune response, right? Because we have to talk about osseointegration.
Oh, osseointegration is fascinating.
This was discovered somewhat accidentally in the 1950s by a Swedish researcher named Per-Ingvar Brånemark. He had inserted titanium optic chambers into the femurs of rabbits to study blood flow.
As one does in a lab.
Right, standard lab procedure. But when the study concluded and he went to remove the expensive titanium instruments, he found he literally couldn't get them out. The rabbit's bone had entirely fused to the metal.
And Brånemark's discovery revolutionized orthopedics. Because what happens is osteoblasts, those are the cells in our bodies responsible for synthesizing new bone, they actually migrate to the microscopic rough surface of that titanium dioxide layer.
So they latch onto the ceramic shield.
Yes. They lay down calcium and phosphate directly onto the oxide shield, physically anchoring the living bone to the artificial implant. It forms a direct structural and functional connection.
It is a profound duality when you think about it. One single element bridging the gap between heavy, high-velocity aerospace manufacturing and delicate living human biology. It solves the aerodynamics of the sky and the orthopedics of our skeleton.
And it really is a remarkable bridge. But, if we zoom out and look at the global supply chain, this raises an incredibly practical question.
I know exactly where you're going with this. If titanium is this perfect, lightweight, indestructible, biologically safe miracle metal, why isn't the whole world built out of it?
Right.
Why aren't our bridges suspended with titanium cables? Why isn't every commercial car frame made of titanium?
The barrier is strict economic reality. Perfection comes with a massive premium. Remember the Kroll process we detailed earlier? Using chlorine gas, extreme heat, and molten magnesium.
Yeah, the toxic nightmare.
Exactly. Unlike a blast furnace producing iron, which can run continuously 24/7, the Kroll process is a batch process. You have to seal the reactor, run the reaction, let it cool for days, break open the reactor, and literally chip out the titanium sponge by hand.
Oh, wow, by hand.
Yeah. It is incredibly energy intensive, it's incredibly slow, and therefore heavily expensive.
Which firmly positions it as a premium elite material. You aren't going to use it for structural rebar in a concrete building.
Its application is strictly reserved for engineering problems, where its unique properties absolutely justify the exorbitant price tag. You see it in high-performance sports equipment, like professional racing bicycles. You see it in chemical processing plants, where highly corrosive industrial acids would dissolve stainless steel in weeks, and you see it heavily deployed in marine engineering.
Right, because of the salt water. The chloride ions in the ocean are notorious for destroying metals.
Seawater is essentially liquid sandpaper to most alloys. The chloride ions break down the protective passivation layer on standard steel, leading to rapid pitting and rust. But titanium's oxide layer is thermodynamically stable against chlorides.
It just ignores the salt.
Pretty much. You can leave a piece of titanium at the bottom of the Mariana Trench for 50 years, and it will look exactly the same when you pull it up. That is why critical naval components and the pressure spheres for deep-sea submersibles are cast from titanium.
So what does this all mean for the future? Are we permanently stuck paying a massive premium for this metal? Is it forever going to be this elite, inaccessible material reserved strictly for fighter jets, deep-sea subs, and medical implants?
Well, the manufacturing world is currently undergoing a structural revolution that is fundamentally altering titanium's economic equation.
Yep.
And it revolves around additive manufacturing.
Additive manufacturing. So we are talking about highly advanced 3D printing. And for an audience that understands the basics of 3D printing plastics, making the leap to 3D printing titanium introduces a whole new realm of engineering challenges.
It is a massive leap. Traditionally, the aerospace industry has relied on subtractive manufacturing. You start with a giant, highly expensive solid block of forged titanium, and you machine it down. You cut, drill, and carve until you are left with your intricate part.
Which introduces a concept aerospace engineers call the buy-to-fly ratio.
Yes.
Because if you need a 100-pound titanium bulkhead, you might have to buy a 1,000-pound solid block of titanium and literally carve away 900 pounds of it. You are turning incredibly expensive, energy-intensive metal into a pile of floor shavings.
Or swarf, as they call it. The waste is economically agonizing. But with additive manufacturing, specifically, direct metal laser sintering engineers bypass the block entirely. We use microscopic titanium powder.
Okay.
A high-powered laser melts the powder, fusing it layer by microscopic layer from the ground up. You only use the exact volume of material required for the final geometry. The waste drops down to virtually zero.
But wait, because of that relentless oxygen affinity we talked about, you can't just run a titanium laser printer in an open room, right?
Oh, exactly the opposite. If you heat titanium powder with a laser in open air, the powder would either heavily oxidize, becoming a useless brittle ceramic, or literally ignite.
That would be bad.
Very bad. So these massive industrial 3D printers have to operate inside sealed vacuum chambers flooded with inert argon gas to protect the metal while it prints.
But the design possibilities that unlocks are just staggering. Because we are building layer by layer, engineers are no longer limited by what a drill bit can physically reach. We can print internal, complex geometries that were previously physically impossible to manufacture.
Yeah, in aerospace, that means printing engine turbines with internal cooling channels curving inside the solid metal, making the engine significantly lighter and more thermally efficient.
And in the medical field, it takes osseointegration to a whole new level.
It really does.
We aren't just giving a patient a solid, heavy titanium hip replacement anymore. Hospitals can now take a patient's CT scan and 3D print a custom titanium implant. And rather than making it solid, they can print it with an internal porous lattice structure that exactly mimics the trabecular honeycomb structure of human bone.
Which is brilliant because it reduces the weight of the implant and encourages the patient's living bone tissue to grow deep inside the artificial matrix.
Wow.
It creates a seamless mechanical gradient between human tissue and engineered metal. We are essentially printing synthetic bone out of a material forged in the stars.
When you step back and look at the entire arc of this journey, it really does read like a cinematic epic. I mean, we are talking about an element whose very atomic structure was fused together by massive cosmic processes, by ancient supernova explosions, long before the Earth's crust even cooled.
It is significantly older than our planet.
It just sat there in the dark for eons, hiding completely unnoticed in a quiet Cornish stream. Then, an observant clergyman and a series of relentless chemists spent over a century trying to pick its chemical lock.
Until they finally broke through.
Right. Wilhelm Kroll finally breaks those bonds, unleashing it onto the world stage just in time to shape the geopolitical balance of the Cold War. It gets forged into the SR-71 Blackbird, tearing through the thin upper atmosphere at Mach 3. It plumbs the crushing, corrosive depths of the ocean. And eventually, through biological serendipity and modern lasers, it finds its way into the most intimate place possible, placed safely inside the human body to heal us.
It is a remarkable testament to persistence.
Yeah.
And I think element 22 leaves us with a lingering, just really provocative thought. Titanium reminds us that the most powerful, paradigm-shifting materials for humanity's future aren't necessarily waiting to be discovered in some distant galaxy or deep space asteroid.
You're right here.
They're likely hiding in the most ordinary overload rocks right now.
Yeah.
We spent centuries kicking black sand because we didn't have the chemical key to unlock it.
Mm-hmm.
You really have to wonder, what other incredible world-changing secrets are currently trapped in the dirt beneath our feet, just waiting for a new process, a new idea, and the right human mind to unlock them?
It really makes you look at a simple handful of river sand in a completely different light. The potential is literally endless. And the wildest part of this deep dive is that element 22 is just one single story.
Just one.
The periodic table still has 96 more natural elements waiting to be uncovered, and I promise you, the very next element on our journey holds a secret that is even more surprising than this one. Follow for the next element and like this episode if you enjoyed the story.